right, folks. I want to show you one last way of doing synchronization before we move into a discussion about classical problems involving interprocess communication, synchronization, race conditions, and stuff like that. So this last way is a technique that you would find if you were programming in Java. So one thing that's kind of cool about this example is it both shows how you can use threads in Java, which you might be curious about, right? We know how to create threads using pthreads in C++, but there's an equivalent way of doing threads in Java. And so what I want to do is I just want to re-envision the producer-consumer problem, but we're going to do it with Java instead, all right? So I've got this solution that's already done, but I want to build the solution with you. So I want to look at item.java. And what I'm going to do is, this is actually pretty cool. So I've been experimenting with a new editing environment with the freshman called Codio, which is really cool. So it's basically a completely online IDE, and it has a built-in shell. You can see here, this is a Linux shell. So this is different than the virtual machine. And I'm kind of liking the price model for it too. It costs students about a little under $50 for a semester, but then you can use it as much as you want. I'm just not sure how powerful the shell is. I mean, it is a Linux, Ubuntu Linux virtual machine. It just seems to be missing some of the parts that I'm used to, but I think you can install additional parts. But anyway, that's not really what we're here for. What we're here for is we want to write some code. So I'm going to put item.java in here. So I'm just copying this from code I already wrote, and I just want you to see what item.java looks like. And I'm going to create a tar file that contains this. So you can just download this tar file. If you're kind of writing code along with me, you can just download this tar file and use it. But basically, it consists of an item class with a ticker member and a price member. And the constructor is set up so that we generate a random ticker and generate a price. The random ticker consists of kind of a clever way of concatenating 3 random characters to create a string. So there's a lot of code here, but effectively what we're doing is taking the ASCII value of the capital letter A and generating a random number between 0 and 25 and adding that to A. So we'll get a value that's A to Z effectively. So that we're going to generate 3 random characters and make that our ticker string. And then we're going to generate a random price between 0 and 99. All right, and that's our price. The one thing that's missing from this that would be nice is to have a toString method. So I'm going to add that public string toString so that I can just do a system out print line when I want to dump this. And we'll return the ticker plus a space plus the price. All right, so pretty straightforward method there. And then the other thing is I don't like the indentation here for all this. That all should be indented. And I don't like the indentation here either, so we're going to indent that as well. Okay, so now everything's indented nicely. Life is good. And we can compile this just to make sure it won't run, but we can compile it. Just press that button and it looks like it compiled okay. All right, cool. It didn't run because I don't have a main program in item. All right, well, why don't we write a main program? So let's create a new file called main.java. And we'll say public class main. Oops, Mina. That's kind of cool. All right, public class main and public static void main string args. Okay, so that's our main program. And what we like the main program to do is we want to create a producer object, and we want to create a consumer object. And we want those two objects to basically work. Like we want the producer to produce stuff, the consumer to consume stuff. So the way that we're going to make this work in Java is we're going to have the producer object and the consumer object both be threads. So they'll be separate threads from the main program. So slightly different than the semaphore version that we just did, where we had a single P thread that was sort of like the child thread, and then we had the main thread that was the producer. So the main thread was the producer, the child thread was the consumer. Here, we're gonna have the main thread just sort of operate on its own, and we're gonna create a producer thread and a consumer thread. So this is pretty cool. If you want the producer to go off and do something, you just say p.start. And if you want the consumer to go off and do something, you say c.start, and that's it. That's all you have to write. So it's a nice short main program. Now there's a little bit of work that we have to do when we create the producer and the consumer so that when you say p.start, it actually works. And I'll show you what that code looks like for that in just a second. But that's pretty much it for the main. Gotta love Java. It's a little bit shorter and sweeter than what we have to do with C++. Okay, so that takes care of our main program. So let's write the producer. Whoops, I must have misspelled it because it doesn't like it when you do that. There we go. All right, so I'm just gonna grab this code here just for starters. And we're gonna have to make some modifications. So in order for the producer to work, so that when you say start in the main program, it actually does something, what we have to do is we have to inherit from thread. So that's pretty much the mechanism that allows Java to do threading. If you want to do threading, you create a class and you have that class inherit from thread, right? And then the other thing that you do is you create a special method that is called the run method. So the run method is also required. So if you create a thread, something that extends thread, then you must implement run. So run is the method that gets called when you say start. So we're going to create a producer object, and then we're going to say p.start. When we say p.start, that's going to run this method, the run method, and that's going to run in a second thread that's independent from the main thread that's invoking start. All right, so the code we want in run is the code that makes the producer do the work that it's supposed to do. So while true, what we're going to do is create an item. And then we're going to insert the item. And how this works, we're going to figure that out in a second. Right now, we have to work on that a little bit, because one thing that's critical is whatever we do with insert item, there's a data structure that the producer and the consumer both have to share in order for insert item and remove item to work. All right, so we're going to figure that out in a second. But I just want to show you how simple the producer class is. It's actually quite nice. All right, now the consumer class looks very similar to this. We're going to have good parallel form. That's a sign of a good programmer. I like to think I'm a good programmer. I think I'm a pretty good programmer. So when you have code that looks really similar, when you're following similar patterns, that's really nice. Try to use consistent naming, try to use consistent patterns of execution. That's all good stuff. All right, so I'm going to create a consumer.java. Oh, that's really interesting. So somehow it put this in a special subfolder, which is wrong. So we'll fix that. Yeah. We'll skip it for now. Got a little distracted. Let's get this written and then we'll move the files around. Okay, so this is our consumer thread. And what it's going to do is it's going to say item the item equals remove item. And that's pretty much how that works. And then we'd like to print out the item once we've removed it. And then we're going to say right here, system.out.println consumer. And we'll print out the item. Okay, cool. So the toString method that we implemented in the item will take care of converting that to a string and printing it out. Fantastic. Now we still have to figure out how remove item and produce item or insert item are operate so that they're sharing the same data structure. All right. But that's kind of that's the basic idea behind how the producer works and how the consumer works. Okay, cool. So, all right, so we have a little bit of work to do here. And so the work that we have to do is we have to figure out how the producer thread and the consumer thread can share some data, right? They have to share this buffer that the producer is filling up with data and then the consumer is removing data. And so the way we're going to do that is we're going to create a special data structure called the monitor, all right? And the monitor is going to be responsible for two things: managing the data structure that allows the producer and the consumer access to the circular buffer, and then also doing the synchronization on the data structure. So in a cool way, both the producer and the consumer have no idea that the buffer is shared. So let's just look at the producer, for example. When the producer does an insert item, it has no idea that this insert item buffer is shared between it. I'm sorry, the item buffer is shared between it and the consumer. And so it doesn't worry about synchronization. It doesn't worry that it's in a, this is really a critical section. It doesn't worry about any of that. Same thing with the consumer. When the consumer removes an item from the item buffer, it doesn't worry that it's a circular buffer or how to manage that buffer or that it's being shared with the producer and that there's synchronization that has to happen because this is a critical section of code. It doesn't worry about any of that. It just says, hey, give me the item. So that's really nice procedural abstraction. So all of that magic and the bulk of the work that we have to do is here in the monitor. Okay, so here's the monitor. All right, so a couple things that the monitor has to have. One thing is it has to have the buffer, the circular buffer that we're using to manage all the data. So I'm going to create, I guess we can just say final int buffer size equals 1000. And then we're going to have a private buffer. I love saying butter, it's making me hungry. All right, so we're going to have a buffer, and that's going to be equal to new item. All right, so that's our buffer. And then we're going to have, just like we had in the semaphore example, we're going to have a private integer add, which will initialize to 0, and a private integer remove, which we're going to also initialize to 0. So add is in charge of figuring out what is the next location where we can add an item, And remove is in charge of keeping track of what is the next location where we can remove an item. And then we have one other special variable and which is, let me think about this. So yeah, which is count. So count keeps track of the number of items that are in the buffer at the moment, all right? So if count is 0, it means that there's no items in the buffer and the consumer can't read anything. And if count is bigger than 0, then it means there's some things that the consumer can read. And if count gets to be buffer size, then it means that there's no room for any more items in the buffer because the producer has produced too many. We have to wait for the consumer to catch up. So count is effectively going to keep track of the number, or sort of like how full the buffer is. When it's equal to buffer size, it's full. When it's 0, it's empty. Anywhere in between, the producer can add things, the consumer can remove things. But we have those special conditions, special edge conditions when the count is 0 and the count is 1. All right, cool. So why don't we then write the code? So first of all, if the producer and the consumer can both share this monitor, we're going to be in good shape, right? So let's do that actually. Let's set things up so the producer and the consumer both share the monitor, right? So to make that work, let's go to the main program. And right up here, we're going to create a monitor. Okay, so monitor m equals new monitor. So we've created a new monitor. And when we create the producer, we're going to pass in m. And we create the consumer, we're going to pass in m. And now this object m, which represents the circular buffer and things that are managing the circular buffer, is shared between the producer and the consumer. All right, so let's write the code for insert item, and we'll write the code for remove item. All right, so there's insert item and remove item. Okay, cool. So let's write the code. So public void insert item, and it takes an item as an argument. All right, so the code to do this insert works exactly the way the code to do the insert was for semaphore. So we're just going to say buffer sub add equals item, and then we're going to add 1 to add, but we're going to do it in a smart way, modding it with buffer size, and that will give us that wraparound, right? If we add past buffer size, when we mod by buffer size, we'll drop that value back down. So we're always going to be between 0 and buffer size minus 1 with that expression. Now, in addition to that, we're going to add 1 to our count. All right, cool. That's our insert item. And now let's do remove item. So we're going to return an item when we remove an item. We don't take any arguments here. And we're going to say buffer sub remove. So we're going to say int result equals buffer remove. And then we're going to say remove equals remove plus 1 mod buffer size, just like we did with add. And we're going to subtract 1 from count because now we've removed an item from the buffer, so we want to reduce count. So count goes up as we insert items, count goes down as we remove items, and we have these 2 separate indices, add and remove, that are keeping track of where to insert the next item and where we're going to remove the next item. All right, now, if we ran this code right now, would we have a race condition? What do you think? Oh, I see one little thing I forgot here. Return results. Got to do that. Would we have a race condition? Like, could we even run this? I'm kind of tempted. I mean, let's run it and see what happens. I'm a little curious. Oh, yeah, we've got a little bit of problem here, which has to do with these files that need to be moved here. Let's see. We'll just rename this. Can I rename that? Let's look at the silly. All right, it looks like I'm gonna have to get a little bit of control here. So let's do an ls. So move producer.java to delete me. Somehow I created a folder called producer.java. All right. Okay, cool. Now we're in good shape. All right, so let's take main and compile it. It should compile everything else. Oh, yeah, we have to fix the code in producer.java and consumer.java. All right, so let's just review where we're at here. So we have the beginnings of code for monitor working that do an insert item and a remove item. I'm asking a question if we have a race condition. By the way, I think we do, but we can talk about why in a second. But let's get the code for producer and consumer working. So the one thing that's missing is we need a constructor that handles the monitor. So the producer is going to have a monitor, and we're going to have a constructor public producer, and it's going to take a monitor m, and then we're going to say this dot m equals m, and then we're going to do something really similar for the consumer as well, just to store our monitor. Okay, so let's try compiling and running that. Oh, the other thing that we need to do is once we have our monitor, we need to be able to use it. So we're going to have an m.remove item. That's where remove item is actually going to execute. So we don't have to have that as TBD anymore. And let's go to producer, and we'll say m.insert item. And this isn't TBD anymore either. All right, and now I think we can compile and run this. Oh, okay, I have another little bug. You probably saw that and you're like, Bob, change it. All right, cool. Let's compile and run main. Oh, looks like I have one little error on my item.java. I need to have, oh, in consumer, I need to put a semicolon there. Let's go back to main, compile and run this. Cool. All right, so things seem to be printing out okay. The question is, do we have a race condition or not? It's kind of cool that it's running. Let's take a look at our code for producer and consumer. Actually, for monitor, really. Okay. So, got notifications from that Gale Force win thing. I might have said this before. I'm so happy with my friends. I've got like two groups of really interesting friends, actually three groups. I have my friends that are scouting friends. They're just really fun to hang out with and go on adventures with, like hiking and biking. And I don't know, tomorrow I might go clamming. I don't know. And then I also have a group of Dungeons and Dragons friends, and they're so much fun. And I know tomorrow night I'm going to be playing Dungeons and Dragons with them, so I'm really looking forward to that. And then I have this other group of friends that are sailing friends. And so I'm just really grateful to have all those really cool friends. And I hope you have really cool friends too. All right. But sometimes when I'm doing a lecture, I don't want to see their messages. Okay. So let's take a look at this code. Do we have a race condition given we have this class that's called monitor, which is shared between the producer thread, the main thread, and the consumer thread? And so whenever you want to know if you have a race condition, one thing is you can run your code and see if it crashes. It didn't look like it was crashing, so maybe we're good. The other thing though is you have to ask the question, do we have multiple threads of execution? The answer is yes, we do. Do we have those threads with the ability to have read-write access to the same chunk of data? The answer, oh yes. They both have read-write access to a buffer, and in particular, they both have read-write access to this variable called count. So it's possible that at the same time insert item is doing a count of plus plus, remove item might be doing a count of minus minus. And there can be a race condition when that happens, because when you do an increment of count plus plus, it is not an atomic operation. Count gets read into the CPU register, one gets added to it, and it gets written back out. So we could have a situation that looks like this. All right, so we'll say this is the producer, and then over here, we'll have the consumer. I guess we'll have the consumer here. Okay, so the producer's thread reads count into register, adds 1 to count, and let's assume when it reads count into register, the value it reads is 9, okay? At this point, the count is equal to 9. All right, it adds 1 to register. So now register is equal to 10, writes count to, writes register to count. So now count is equal to 10, right? That's how we'd like things to operate. But, interesting. But if we have a consumer thread, things can get messed up. So here's what's going to happen. The consumer thread is also going to read the count into the register. It's going to, instead of adding 1 to the register, it's going to subtract 1 from the register. So now you have the value of 8. And now we're going to write the register to count. Count equals 8. So the question is, what is the new value of count? Is count the value of 10, or is count the value of 8? And are either of those correct? So the answer is it totally depends on the order that these two lines execute, all right? So if we say that, because remember, things don't happen completely simultaneously with shared data. Someone is going to get write access to that data before the other person. So someone's going to do the write first and someone's going to do the write second. So if we were to slow things down and say, well, okay, the consumer thread gets write access to the to count after the producer thread. And so what could happen is that the consumer thread gets to go last, and therefore the final value of count is 8. And that's actually incorrect. If the producer thread is producing an object, increasing the count to 10, and the consumer thread is consuming an object, then the final value of count should be 9, right? We start out with the value of 9, we produce a new object, but we consume an object, we should be back at 9. But we actually are going to be we're going to be at 10 or 8, depending on how things go. So we do have a race condition that's subtle, and you might not see it. You don't see it when things are running, at least right now in the brief time we let it run. But if we let this thing run for like a week, I bet you'd see a crash. The crash would probably be, I would expect that you'd have an index out of bounds error. So the index out of bounds would be count either ends up too high, in which case, actually, let me think about this. No, add and remove will never do index out of bound. But what could happen, and it's very subtle, is that the producer could overwrite items that haven't been read by the consumer, or the consumer could consume duplicate items. All right, that's what's going to happen in this race condition, and it's incredibly subtle because the program will never crash. So you have to carefully monitor every item that gets added to the buffer and every item that gets removed. And if you're a sloppy programmer, you might miss that and ship this product, and all of a sudden, folks are getting bad stock market quotes and getting really angry. And it might be like 2 months before someone discovers the problem with your software. So I have had personal experience with very, very tricky race conditions that have taken me weeks and weeks to debug. So one way that you can attack debugging race conditions is to go, let's run it and see if it crashes. That is not a good way. The best way to do it is to ask yourself that question: do I have more than one thread sharing access, read-write access to data? And if the answer is yes, then you have to have some kind of synchronization in place, or you are going to have race conditions. Bad stuff's going to happen. Okay, so like when I grade the homeworks that I'm going to assign to you in the near future, we'll have a few assignments coming up that are going to involve writing code to deal with race conditions. I am going to run your code, of course, to see if it works or not, but I'm also going to go through your code and look to make sure that you are actually accounting for race conditions and doing synchronization in your code. Okay, so we actually have to do this now. We have to put some synchronization around this. And actually, it's incredible what Java has. It has this technique called monitors, which is a really cool way of dealing with race conditions. And here's how it works. What you do is you call the method that you're writing a synchronized. Let's say, oh no, we do that here. You say that a method that you believe effectively encompasses the critical section of code that you want to run, the section of code that you want to have protected, you call it a synchronized method. And the rule is for synchronized methods that while you're in this synchronized method here, no one else is allowed to call another synchronized method inside this object. So if you're in insert item, then consumer is not allowed to go into remove item. It's blocked. All right, so this is brilliant. This is totally brilliant. This is amazing. And the cool thing about this synchronized method is that it, just like semaphores, you do not have to worry about busy waiting, because if you go into insert item as the producer and the consumer tries to go into remove item, it will be blocked, but it's not a busy wait block. It's basically put to sleep. So this is amazing. So if I compile and run this, I may not see any difference. kind of impatient here. Oh, I see. I kind of want to compile and run my main. All right, let this run. It looks like we're almost done. I'm kind of stalling there. You know, I would say that for the most part, Codio really rocks. It is super, super reliable, and it's just so cool to be editing stuff using the browser. And I think it's made things easier for the freshmen, which is awesome. But I'm not really happy about what it's doing right now. Huh. Yeah, I'm not really sure what's going on here. Okay, well, let's do this. I'll just log in again. I just created a special, oops, that's not the right place. Let's go back to the, yeah, lecture notes and projects, and then we'll find the operating systems one. Go to main and try compile and run. This will probably work a little faster. There we go. CD CD operating systems, and we'll do that. Okay, cool. All right, so the program's running. I don't know if you noticed, but it does look like it's running a little bit slower. And that's because now we have some synchronization in place. So the producer and the consumer can't just go crazy. Whenever the consumer wants to read something out of the buffer, it's going to block if the producer is writing something to the buffer. Okay. All right, so we have one situation though we have to watch out for. So let's take a look at producer, or let's take a look at the monitor and think about this for a second. We do not want to insert an item if count exceeds the buffer size. Because if count exceeds the buffer size, it means that the buffer's full. And if we insert any more items, it means that we're going to overwrite the buffer. So we need to hold count back a little bit, or hold insert item, pause insert item if the buffer is full. All right. So if the buffer is full, we are going to do something special. So if the buffer is full, we are going to go to sleep. And we'll look at the code for sleep in a second. All right, we have a similar situation over here in remove item. If the buffer is empty, oh, I didn't mean to say buffer equals buffer size. I want to say count. If the buffer is empty, in other words, count is equal to 0, then we want to go to sleep. Okay. Now, let's think about this, all right? So let's assume that we're starting out, all right? And so insert item gets executed, and at the same time, remove item gets executed. All right, we have not even put an item in the buffer yet. So insert or remove item is gonna execute this count equals 0, and it's gonna go to sleep because the count is 0. We haven't put anything in the buffer yet. On this side though, insert item is gonna say, all right, count is not equal to buffer size because we haven't added any items yet. And it's gonna add an item, and it's gonna increment count. Now, what we want to do is after incrementing count, we actually want to do a check. If count is equal to 1, then it means that we just went from count equals 0 to count equals 1, so we need to wake up remove item. Why is that? Well, I just gave you that scenario, right? Insert item and remove item run at the same time. Insert item, and we're starting at the beginning of the program, so count is 0. Insert item says, nah, count is not equal to buffer size, so I'm not going to go to sleep. At the same time, remove item checks to see if count is equal to 0, and it is because we were just starting out putting stuff in the buffer. So we're going to go to sleep. All right, so remove item is now asleep. Now, while remove item is asleep, oh, you know what? I sort of misspoke because I said something special last night. Let me rewind this for a second, okay? Okay, let's assume that we just started the program, all right? So the buffer is empty, count is 0, and we run, and the consumer gets to go first. So the consumer jumps into remove item and checks to see if count is equal to 0. It is equal to 0 because we haven't put any items in yet, so it goes to sleep. The moment it goes to sleep, it basically releases the synchronized control of the method. We were sort of still in remove item, but we let go of the lock that we have on blocking other synchronized methods from executing. All right, that's what's critical about this sleep. And so because we release that, it allows insert item to run. So insert item runs and says, is count equal to buffer size? No, it's not. Let's add an item and increment count. And now we say if count is equal to 1, what we want to do is do something called notify. So notify is going to wake up the remove item method if it's sleeping. Otherwise, it gets ignored. So in our example, remove item is sleeping. It was on the sleep command. This notify right here wakes up remove item right after the sleep method call. And so then remove item can then remove the item that was just put into the buffer. And then count goes back to 0. All right, we have a similar thing that's happening on the insert item side. Let's assume now that insert item's been running like crazy, and now it has completely packed the buffer full of items. So now we go to insert a new item, and count is equal to buffer size, which means we have a completely full buffer. So we're going to go to sleep. And so insert item releases the synchronized block on other methods that are synchronized within this class. And when remove item gets called by the consumer, it's allowed to go in. It checks to see if count is equal to 0. It's not because count is equal to buffer size. It removes an item and decrements count. And so what we have to write here is kind of a method that parallels this, right? I'm actually going to copy and paste that here. So I'm basically checking to see, is the new value for count equal to buffer size minus 1? If it is, it means that we would just went from a full buffer to a buffer that's partially empty. There's room for one item to be put in. And if that happens, we're going to do a notify. The notify is going to unblock the sleep here in insert item, and insert item can continue executing. Now, if insert item, we're not in insert item and we're not blocking on sleep, and we do this notify, it basically just, it's like a tree falling in the woods, no one's around to hear it. The notify just gets discarded. All right, so this is really cool. This is actually a much more powerful version of the code, because prior to having this sleep block and the sleep block, it was possible for an insert item, for example, to overrun the buffer by having a count value that's bigger than the actual number of items that's allowed to be in the buffer. And we could overread the buffer by having a count value that was negative, which means that we're recycling items that are in the buffer. But now with the sleep, we're preventing that from happening. Count can't drop below 0 when we're moving items, and it can't go above buffer size when we're inserting items. But this is also done in a really nice way that frees up the synchronized insert item method. It's like we're doing kind of a late return from the insert item to allow remove item method calls to be executed. Now, the only thing we have to do to make this work is write the code for sleep. So there's a special sleep method that we're going to have to write. And I'm just looking through my notes here to make sure I get that code. I'm pretty sure I printed it. Oh, come on. Really? All right, so the beginning of it is this. Private void sleep. And I'm going to look it up here. I downloaded it to JGrasp. Oh, let's go over here then. All right. Where's my sleep method? Here we go. So the sleep does something called wait, which is very similar to, it's just a different name for sleep. All right, so we'll just write that code here. And we've got a catch exception. Might as well just print something out here. System.out.println. I think it's I think we'll just do that. Tostring, I don't know. How do we print out a Java exception? Oh, thank goodness there's all this cool stuff. Yeah, we can just say E. Okay, cool. And I just want to get the indentation correct here. Nice. I don't like that try there. That's better. Okay, cool. So sleep is basically hiding that we're doing a wait call. So we could just do a wait. But the nice thing about doing it this way is that we're catching the exception and dealing with it, and we don't have to deal with the exception here in our remove item code or our insert item code. All right, let's go to main Java, compile and run. Oops. CD to operating system. And we'll compile and run this. Cool. So that's really awesome. So now you might be asking yourself, geez, Bob, last word. So first of all, you might be saying to yourself, boy, Bob, this Codio stuff's really cool. Can I use Codio for operating systems projects? And the answer is, I'm not comfortable with that just yet. I think I'm, for the rest of this course, I want to continue to use the virtual machine because I know that that works. But I am going to kick the tires and try it out probably in web programming. And if it works really well in web programming, maybe in future classes we'll use Codio instead of the Amazon Web Services, because I know that the price of Amazon Web Services, you pay a bit each month. And so this is a really nice way of controlling costs because you're paying, I think it's like $46 for the entire semester. So, all right, that's it for monitors.